Hi, I'm Noah, and this is my capstone project. I've always wanted to work in science and engineering, and have been inventing things for a while. As a young child, I designed electric circuits, built toys with cardboard, and later prototyped inventions aimed at solving real-world problems. While I have recently structured my life around becoming an engineer, having been accepted into the University of Waterloo to study mechanical engineering, my dream career is inventing, which I would like to pursue if given the chance. I've already developed many skills in these areas. I'm proficient in 3D design, circuit design, and have previously used high-level physics and mathematics in projects. While I'm well accustomed to making various projects, for my capstone, I wanted to do a more thorough look into the intricacies of inventing, specifically the patent process, prototyping, and product design. My essential question for this project was, what skills must I learn in order to patent and sell my inventions, with my goal being to work through these steps, culminating in the creation of a design and prototype ready to be patented and sold. To first patent an invention, you need an invention. I started by narrowing down ideas, starting with a document of all my inventions since grade 6, and I needed my chosen invention to fit the following criteria. It must be patentable, and prototyping and testing must not be prohibitively difficult. Firstly, what makes an invention patentable? According to the Canadian Intellectual Property Office, patentable inventions must be unique, meaning no slightly altered copies of existing inventions, useful, and non-obvious to somebody working in the field. This eliminated several of my earlier inventions that were far too close to existing ideas or had no real purpose. Some examples include my old wave power generation ideas, carbon capture ideas, or things like arrow launchers. I then eliminated anything that I thought would not have a viable chance of being prototyped before the end of the year. This included some of my grander inventions, like geothermal drilling rigs, missiles and aircraft, and industrial chemistry equipment. In the end, I was left with 2 inventions that I thought could make a good capstone project. One was a more efficient process for refining silver, and one was a cheaper and more compact artificial skylight. I decided to do significant background research on both of these inventions. For the skylight, I looked at existing patent designs online, all of which worked differently than mine but provided useful insights into some of the steps. I looked at other lighting solutions as well, learning what I could about the qualities of sunlight that an artificial light must mimic. For the silver refining process, I substantially researched the existing method, calculating its energy, resource, and cost efficiencies relative to my own process. In the end, I settled on prototyping the skylight, as the silver refining process would require more effort. I still hope to work on it during the summer. You may be wondering, what is an artificial skylight? And also, how is my design different than anything else out there? Firstly, an artificial skylight is a light that mimics sunlight by being highly collimated, meaning the light does not spread out. As you can see with a normal lamp, the light rays spread out. If you were to place an object here at this point, the shadow at a further distance would be larger than the actual object. So with the sun, there is a lot of space between where the sun actually is and where the Earth is. So if you were to place an object at one point and then move it a relatively small distance further away, I guess its shadow would stay the same size between those points when viewed from a fixed wall, say here. Now the goal of an artificial skylight is to mimic the collimation of the sun, where the light rays are all moving parallel, and where a shadow of an object held at one point relative to a wall on another point would have a shadow the same size regardless of where it is held. It also mimics the Rayleigh scattering that takes place in the sky, which makes it blue. While other designs use complicated systems of Fresnel lenses, mirrors, and large light sources, my design uses an array of small, simple reflector dishes and LED lights. This design is partially inspired by the YouTuber DIY Perks. Here, he uses a setup to mimic sunlight using an LED with a large mirror to collimate the light. He also uses a dust-filled water layer to mimic Rayleigh scattering. His design, shown here, is very successful at producing the desired effects, It is barely noticeable that this is an artificial light source rather than actual sunlight. Of course, this was my goal. In most ways, my design is the same, though it is shrunk down and multiplied. I started my prototype with the LED array, cutting plexiglass, soldering the LEDs, and adding power wires. My next step was to 3D model the reflector. An important consideration to make here is how big to make the dishes. Making them smaller would increase the brightness, as I could use more LEDs in the same area, but doing so would also spread out the light, decreasing its collimation. The spread of the light can actually be roughly calculated by finding the angle taken up by the LED from the perspective of the bottom of the reflector. I chose the dish size I did as a balance between brightness and collimation. So picture this reflector here. We have a known distance from the LED to the base of the reflector and a known width of the LED. Since the angle of incidence, or the angle at which the light hits the reflector, is the same at which the light bounces off from it, the difference in angles between the reflected light rays coming from one edge of the LED relative to the other will be the same as the angle between the two incoming light rays to the reflector relative to one point from each of the edges of the LEDs. So this angle here will be the same angle here, which then, when the light impacts a back screen, will determine the size of the apparent image here. This can be calculated as the inverse tangent of these two lengths. I then assembled the reflector, case, and power electronics, which I'll show you in another quick build montage. Ta-da! With my light working, I only had to mimic the Rayleigh scattering that gives the sky its signature blue color. In the DIY Perks video, a thin layer of soapy water is sandwiched between plexiglass plates. This mixture of soap and water is called a colloid and has some interesting properties. Most importantly for artificial skylights is the Tyndall effect, where light is scattered unevenly. Blue light is scattered more than red light, mimicking the scattering that occurs in the sky and making the artificial light appear even more like a window. For my design, I tried using powder dye filled epoxy. For some reason, I decided to use whiteout, which contains titanium dioxide powder, instead of literally any other white powder I could find. Unfortunately, it reacted with the epoxy, making some larger flakes and emitting a smell that probably cost me a few years of life expectancy. With the epoxy finally cured, my prototype was done. So, how well does it work? Well, to be honest, it's a mixed bag. Starting with collimation, the light emitted from my prototype doesn't spread out as much as light from a normal lamp. It's definitely nothing like a true light beam, however. As for the Rayleigh scattering, the dusty epoxy has a nice effect, but once again, it's not exactly what I was going for. It's clear I still have a lot of work to do. Despite this, my prototype works well enough that it could definitely be used in a patent application or to pitch my invention to investors. It also found a new role in my house as a plant light, as my parents like the quality of light it gives off. I've learned a lot throughout this process. Talking specifically about my invention, if I were to make another prototype, I would improve collimation with larger reflectors and brighter LEDs. I would also improve Rayleigh scattering with proper powder dye rather than whiteout ink, and I would try to improve the quality of my reflectors as the aluminum foil I used was quite rough in some places. Overall, I would also say that this project has furthered both my invention research skills and prototyping skills. I've also somewhat improved my 3D design skills as this project was made to look quite a bit more professional than my previous projects. Regardless of the somewhat mediocre successes, this project was quite fun to work on. It challenged my existing skills, built new ones, and made a starting off point for further work on my light array invention. Alright, that's it. Thanks for watching. Goodbye.